Yes. Yeah, if you have any question, unmute your microphone. Tell other. I am hearing a lot of background noises, so I muted all of you. If anything, you can unmute and ask me. Okay. The magnetic properties, as I mentioned in the previous class, that is basically there are two things. One is a spin-only magnetic moment, that is spin-only, and another one component is there, angular. There are two components. Okay, so as I have briefly mentioned in the right hand side, as also I already mentioned that the electron spins its own axis as well as it spins around the nucleus. As a result, there are two contributions in the total magnetic moment. Right, I am not reading all these. These are the very fundamental. The spinning electron generate the bulk of the magnetism in an atom. That's the fundamental principle. Now, so there are two components, not only spin component, but it's also the angular momentum. That is, that it rotates around the axis as well as around the nucleus. So there are two contributions for the magnetic moment for the complex or the sample that we consider. Right? Very simple. Right? You can follow here one. Right? So we are talking about the spin-only magnetic moments. This is one of the success stories of crystal field theory. There are two success stories. The main contribution, that is, for the crystal field theory, is one is the color of the complex. We have already studied. Second one is what we have, the magnetic properties. Right. So this is very important. This is the magnetic property using crystal field theory is not necessarily the 100% success, but to some extent. Say, for example, first row transition metal complexes. I hope you understand, right? We talk about the first row D block element, titanium to copper, right? Titanium to copper. These complexes, the magnetic property of these complexes can comfortably explain with the help of the crystal field theory. So how do we do that? The magnetic moment, yes, we'll talk about the spin quantum moment. This is the equation that we usually, the original equation, that is we have a mu equal to 2 s into s plus 1, that is a square root. That's a Bohr magneton. So to simplify that, you don't need to go and find out the spin, simply find out the number of electron. This is very similar to, I mean, you should have studied already during your JEE, your preparation. So that finding out the number of unpaired electron. How many unpaired electron is there? Based on that, what you do is you can simply calculate the, keep in mind, this is a spin only magnetic moment. Okay. So now whatever so far what we have studied, that is a high spin or low spin. The concept comes into play here. So if you know whether the complex is a high spin or low spin, you will be able to comfortably find out the magnetic moment using this equation. Basically, what you need to know that you need to know the unpaired electron. So unpaired electron, how do we spell that? Based on the crystal field theory, not based on the hybridization concept that you have studied earlier. You will be making the orbital diagrams and then flip and then you do sp3 d. That is not that, right? Here it is in the case of octagonal complex, what we say is a T2g orbital and EG orbital. How the electrons are distributed between here, how many unpaired electrons is there, based on that you will be able to, you can easily find it out. I think there's a very straightforward, nothing much to explain. Now I have shown the table. Right. So if I know the number of d electron, I should know this, whether it's a low spin or high spin. How do I know that? That's a weak field ligand or strong field ligand. And then I will be able to know how much is the magnetic moment. Right? So in this table, I have given you the possible, the configuration and the calculated magnetic moment and the observed magnetic moment. You can see here up to D5, absolutely, yeah, very close relationship with the calculated as well as the observed. Observed means experimentally measured magnetic moment. After that, yeah, so I mean, if you go there, there is a variation in the magnetic property of magnetic moment that is experimentally observed. That is basically comes from the angular momentum components. Okay. So what simply you have to know? You need to know the d electron configuration. What are the ligand that is complex, the coordinated in the metal center, whether it's low spin or high spin. Find out the unpaired electrons. Apply the equation. That is what I have the n square root of n into n plus 2. From there, you calculate your magnetic moments. Right? That's all about the magnetic moments. I have asked the tutorial teachers to give you enough examples to work out in the class. So they will give you problem and you can work out as many as in the tomorrow tutorial class. The color of the complex, I have already explained to you. There is not much to explain again further. The same slide I'm showing, because why I brought it here is that this is another success story of the crystal field theory, that you can beautifully explain the color of the transition metal complex. Right? I'm not again going to this. All this I have shown already before your midsum. Right? Now I put the question. Right? I have given the answer also. That this is an example. Say for example, hexabin cobalt 3 is diamagnetic and orange yellow in color. On the other hand, hexafluorocobalt 3 is paramagnetic and blue. Right? So now how will we explain? Right? This is a question. I have given the answer. It's very straightforward. But what we have? Cobalt 3 plus, but the ligand is different. One is your strong field ligand, amine, another one is your weak field ligand. Now, yes. Okay, right. Now you can read through it, because already I explained before your when I started and teaching your actual the crystal fields theory and splitting and the color. All this, the color bill I have already explained. Okay, so now you can see that simply what you need to know, that you need to know the d electron. How many d electrons are there? How these orbitals are split. The energy gap between the T2G and EG orbital in the case of your octagonal. If it is a tetrahedral complex, your E and T2 orbital, how the energy gap is there. Anyway, in the tetrahedral we will have we don't talk about the high spin low spin complex. The energy gap is very less. As a result, pairing will not take place first. It will go and fill up all the orbital and then pairing takes place. So looking at the geometry, looking at the nature of the ligand, and then you see what is the color and then what is the magnetic property or the magnetic moment, how you can calculate, right? Okay, moving little there. So this is again, this also I have already explained. I mean earlier before your midsem, I talked about the Beer-Lambert's law, or Lambert's-Beer's law, right? This is the Lambert's-Beer's law that I mentioned in the earlier classes, right? Now you can see here, right? A is the absorbance. Tomorrow, who are all coming to the? Just hold on. Right, it doesn't go well. Yeah, absorbance. That is log I0 by I. That is the incident light intensity, and then to the transmitter light intensity, and then you have a epsilon. That's the molar extinction coefficient, and this is the path length. You can recall I discussed this in the earlier classes. C is the concentration. Concentration. L is the path length. That is the distance at which the light passes through. And epsilon is the molar extinction coefficient. That's a constant. So your first year, when you are going for a lab class, your teacher will be teaching particularly this Beer-Lambert's law. The first experiment is based on the Beer-Lambert's law. Okay. So that is basically why I am bringing is that we are talking about the color. We are talking about the energy gap between the T2G and EG orbital, which in turn, there is a lambda max, the wavelength at which it gives the maximum absorbance. All these are related to your Beer-Lambert's law. Okay, right. Now, Now, now looking at this one, that's all about crystal field theory I have completed. So what you need to understand the crystal field theory, basically, you need to understand the d electronic configuration, the d orbital splitting, what are the factors influence the splitting. So we consider many things: the nature of the metal, the oxidation state of the metal, and your geometry, as well as the nature of the ligand. You can recall in the slide that I have already sent to you. So you will be able to find it from there. I hope all are with me. Yes.
Yes, sir.
Yeah. Thank you. Right. Now, is well and good. The crystal field theory is very good. Right. So far, so good. It can successfully explain the color that the VPT cannot do that. Valence bond theory cannot do that. The magnetic property, that is very good. The valence bond theory make some mistakes, but crystal field theory give you a spin-only magnetic moment accurately, precisely it gives that. But there are issues there. It's not that crystal field theory is completely correct and can explain all the properties of the metal complexes. That's not that. Right. Now, earlier also I mentioned the crystal field theory basically it talks only about the S and P orbital. Sorry, only d orbital, not the S and P orbital. So only d orbital. It is so silent on the S and P orbital. No mention of the S and P orbital. Only talks about the d orbital. So if you really want to understand the bonding and structure, you cannot only consider the d orbital. You also need to consider your S and P orbital. So that is one of the failure, right? And the crystal field theory, right, does not, or I mean, it failed to account for the overlap between the orbitals. I mentioned in the MOT when I taught molecular orbital theory, what it says, what is the symmetry adapted linear combination of atomic orbitals. Here, the crystal field theory is so silent on the overlap. It doesn't say anything about it. Another one very important thing is that all the ligands are considered as a point charges. Point charges. This I have discussed earlier. So if it is if point charge assumption is perfectly correct, then the spectrochemical series must be wrong. But that is not the correct. So the crystal field theory failed to explain the carbon monoxide, that is a carbonyl ligand, that is a strong, or Cn minus as a strong. If a Cn minus is a negative charge, if the assumption of point charge is 100% correct, Cn minus should be strong, and also X minus, the halide minus also should be strong. But if that is not the case, you cannot explain simply with the help of the crystal field theory. These are right, the strength of the ligand and the halides are weak field. Right, this you cannot explain simply with the help of the crystal field theory. These are some of the shortcomings. Of course, each and every theories will have their own shortcomings, drawbacks. But in the subsequently, we'll be able to see that how we can understand the overcome and to explain all the properties of a metal complex with the help of other theory. That is what we call the LFT, that is ligand field theory or modified molecular orbital theory, which is not in your syllabus. Yeah, before going to the organometallic chemistry, let me briefly explain you. Right, metals in low oxidation states. Say, for example, I have a M plus 1, right? Or if I have a M plus 7, right? Let's take M2 plus 2 or plus 1, right? There are two metals. How do we stabilize, right? There are two cases. What I talk about is that if it is the oxidation state is low, that metal center is electron rich. If the oxidation state is high, the electron density is very poor. In chemistry, in coordination chemistry as well as in organic chemistry, these two are too extreme. Stabilizing these two metal center is a formidable job. Unless otherwise you bring some kind of a ligand, you will not be able to stabilize any metal in the plus 2 or your M plus 1. The same way M plus 7 or your plus 6 or plus 8, whatever it may be. right? Now, here what we need is that we need to bring something to explain that, but there are metal complexes with +1 or +7. The +7 typical is your the first two times metal are there, right? Now, how do we do that? Right. There are yeah, I will bring that. Yeah, there are ligands that we need to bring into picture. So that is the where I will bring you the organometallic chemistry, or in other words, what we here say the pi bonding. What we need to bring here is the pi bonding. Again, let me explain. Let me tell you, metal in the low oxidation state or metal in the high oxidation state. One is electron rich, another one is electron poor. No electron is there. So they say D0 or D1, right? Or you have a, so say for example, D0 and then D7. You can compare this. One is electron rich, another one is electron poor. So stabilizing this kind of a system is somewhat difficult. There, what we need is we need to bring a sum of the ligands, which can stabilize this kind of a metal center, either electron rich or electron poor. So that we will see. That's a entry for the organometallic chemistry. And the chelate effect, I think your teachers, your tutorial teachers already taught you about the chelate effect. I hope you attended your tutorial classes. This I will not be covering, right? This is one of the effects, the chelate effect, and what we call the pi bonding. Pi bonding comes into picture to stabilize, right? Your tutorial teacher should have shown the picture of a lobster, that how it capture the food. The same way, a metal center, Mn plus, is complex with the chelating ligands, right? Chelating ligands. It basically stabilizes. There will come across the pi bonding. The pi bonding aspect, I will come into that. I will teach you in the organometallic chemistry, right? So I hope you don't overlook the chelate effect. Chelate effect is important. So you can, if you have not attended, you ask your teacher to provide the notes, or you ask your other student who have attended, because I will not be teaching the chelate effects. Okay, right. So far what we have done is MO theory is over, and then crystal field theory is over. And both these topics are kind of a review of what you have already studied. And not much is new, right? So finding out the MO electronic configuration, and then bond order that you should have studied. The same is the case, crystal field theory also. It is class 12, and in the JE syllabus it is there. So we have, I mean, a kind of a brushing up with additional little bit of input, the Beer-Lambert's law and all other things that I brought in. Okay, so I completed my MO theory and crystal field theory. Now what we'll do is that we'll go to the organometallic and the catalysis. Organometallic chemistry and catalysis. Basically, I'm not sure how many of you have studied the organometallic chemistry. At least you should have heard about the organometallic chemistry. So here, basically, as I mentioned there, the stabilization, all this comes here, right? I will come to the explain you a little later on how this pi acid, pi donor comes there, and then how we see it. So organometallic chemistry is an important area. Is one of the areas in inorganic chemistry that deals with the metal carbon bond. Okay, basically it is a bridge between your organic chemistry and an inorganic chemistry. I will not be able to give you a very detailed introduction. I will briefly mention what actually the organometallic chemistry, what are the compounds or the complexes that we consider as organometallic complexes, organometallic compound. Basically, what you need, what you need to do is that it's the metal carbon bond. What is the metal carbon bond? You can look at this one, right? Metal carbon bonds. That is what we say. That's a primary thing that you need to. So it can be a pi bond, a metal carbon, or it can be also a sigma bond. That also metal carbon bond, right? A pi bond or a sigma bond. I will explain you how we account for all these ones. So typically, look at here. What I have shown here in my left-hand side rectangle, a carbonyl ligand, how it is interacting with the metal center. This is what I am talking about. My left-hand side, right? As I will have a MO diagram. I will show you a little later. You can visualize your MO diagram of carbon monoxide. Let me go. Otherwise, where is it? Just once. Look at here. Look at here. This is the diagram that I have shown when I taught you the hetero diatomics, right, in the MO theory, right? So basically what I have a lowest unoccupied molecular orbital, that is a pi antibonding orbital, and I have a highest occupied molecular orbital, that is a 3 sigma orbital. Okay, I hope you are following. So these two orbitals are being used in making a bond. I will go back. Yes.
So can you show the molecular orbital diagram of carbon monoxide?
You want me to show again? Yeah. Can you?
Sir, highest occupied molecular orbital should be 1 pi because 1 pi has 4 electrons. So it is highest occupied.
Highest occupied in energy level, not number of electrons.
It should be 3 sigma because it is the highest in.
Yeah, I talk about this. I encircling by red color. That is the highest occupied molecular orbital. What's your doubt?
Sir, highest or lowest in terms of energy, not in terms of electron.
Highest and lowest is in terms of energy, not electron. I did not talk about the number of electron. I'm talking in terms of energy.
Okay, sir. Okay.
Right? Don't confuse. Highest and lowest, we talk about the energy, not the number of electron. Right? That will be, if it is a number of electron, that is a big problem. Right? That's not the case at all. Right? Okay. Now you go here. Right? This I explained earlier also. Right. Now you go here. This is what I have shown here. Now look at the sigma bond formation. Right. That is basically what I have shown here. A sigma bond formation, basically, what is that? The sigma bonding orbital is interacting with a metal, that is the highest occupied MO of carbon monoxide, interact or overlap with a metal which has the same symmetry and similar energy, make a sigma bond. On the other hand, there you have your, this is basically sigma donation. Sigma donation from ligand to metal, right? Carbonyl to the metal. On the other hand, and the what I have shown here, that is, say, for example, what I have shown in the blue rectangle, here what we have, the other orbital increase. That is the lowest unoccupied molecular orbital, that is a pi antibody, pi star orbital, right, which is empty, right? Empty pi star orbital overlap with the filled d orbital of the metal. That's what is shown here. Yeah, pi back bond, right? What do you have? What we call that a synergistic effect, right? You should have heard about it. A synergistic effect. That is a sigma donation and a pi acceptance. So this is the basic fundamental in one of the concept here in the organometallic chemistry. This is with respect to only with the carbonate. The same way, there are many other ligands are there. They can either as a pi acceptor or pi donor. It doesn't mean that organometallic talks only about the pi orbital. No, it has a both a sigma as well as the pi. I have given the example donation from pi, my right hand side, and then back donation to pi star, right? So there are several examples like this. Here comes the new topic, that is what we call the organometallic chemistry. I have given explanation, examples. The first one is what we have a ferrocene, that's a well known, and then fullerene, buckyphal, that is bonded to a inorganic metal complex, and a rhenium complex, and then molybdenum complex, that you have a bimetallic organometallic complex. A metal bond is there. Don't worry, these are all not in your syllabus. I'm just showing an example. And then this one, the last one what I have shown is the rhodium complex. Rhodium complex, that is the complex will be using in the catalysis, the Wilkinson catalyst, right? Tris triphenyl phosphine rhodium 1 complex, which is conventionally used as a hydrogenation catalyst. Let's go quickly, right? We'll go here. What all compound? How do we consider? That is basically I'm talking about the metal and a carbon bond. How the metal carbon bond can be formed? What is the characteristic features? Basically, what I have, you can see that C is always more electronegative compared to metal. So there will be a residual negative charge. That's a basic fundamental concept. And obviously, there is a residual positive charge at the metal center. Right? Now, how do we define organometallics? Yeah, you can read from here what I have given here. The bonding interaction either can be ionic, covalent, or a localized or delocalized bonding between a metal and a carbon. Again, this definition is not a hard and strict rule. There are exemptions are there, right? So whenever you see that metal carbon bond, you cannot simply call all of them as a organometallic compound. Say for example, sodium cyanide, right? NaCN. Okay, NaCN. Sodium is a metal. Yeah, you have a CN. Is a carbon is there. I don't call this as the organometallic compound. That's what traditionally you can read it that what I have put in the bottom, right? What I have put traditionally, what will not do is that the metal cyanide complexes are not considered as organometallic. Okay, that's an exceptional case. I mean, those who go for a advanced chemistry, you will be able to understand what actually that means. At your level, that is not required. Okay, let's go a little bit of history quickly. Okay, I hope I am not going very fast because this is a very basic introduction. I'm not asking question and expecting answer from you. I just narrating the story of organometallic chemistry. Then when I go further, I will give you enough time to interact with each other. The first transmetal organometallic compound, Zysalt, right? Yeah, this is the first one that was synthesized. How did they get it? You have your K2PTCl4 minus and ethanol. Yeah, these are accidental discovery by the time, right? So accidental discovery, you get your Zysalt here. That's a K(C2H4) PTCl3. That is a complex that is basically a organometallic. But at that time, it was not named as a organometallic at all, right? This is a typical picture that I have shown on the right hand side. The yellow color crystal are there. So initial discovery was in 1827 by a Danish pharmacist, not a chemist. It's basically a pharmacist, and the structure was established almost 150 years later. 150 years later. Okay. Then I briefly put the history how it comes here. You can read those who are interested. You can go and read this Organometallics 2001. There you will be able to see that how an accidental discovery that leads to the establishment of a new field, that is what we call the organometallic. So as I said, it's not only the pi bond, sigma bond also is there. There is another Edward Franklin that he synthesized another that is basically a alkyl complex. Say for example, double bond C double bond. Yeah, how this is bonded with a metal center, right? So you have here I have given here, right? These are all just for your understanding how the organometallic chemistry field is established. Now it comes here C2H5I and the zinc. Yeah, what we say zinc diethyl. zinc diethyl organometallic compound, how it is basically, who has a student under Robert Bunsen, that you should be knowing who is Bunsen, right? Next, we'll go here. Metal carbonyl. So because we'll mostly center around metal carbonyl or metal triphenyl phosphine ligands. Okay, right. How do we synthesize? Right now, if you look at the left hand side, I have given a picture of a Ludwig Mond. Right, he is the one. There's a father of metal carbonyl. Father of metal carbonyl. Right, father of metal carbonyl, because he is the ones initially synthesized the metal carbonyls. Again, it's not meant to synthesize. It's not a targeted synthesis of metal carbonyls. Yeah, it is basically during the purification of nickel, what we call the, you should have studied Mond process of nickel purification. That is your nickel oxide at 200 degree in presence of hydrogen. You get your impure nickel along with the iron and cobalt, and then what you do is that excess of carbon monoxide, you heat it, you get a nickel tetracarbonyl, right? Nickel tetracarbonyl. Further heated, you get a pure, 99.99% nickel that comes here. So at that time, nobody knows the nickel tetracarbonyl structure. So you can see here the left hand side. I have shown here some of the textbook. If you can get the textbook of this year, 1890, 1930 textbook, will show a funny picture for carbonyl complexes, because nobody was able to establish the structure because of lack of facilities. Right. We'll come back again, right, to the carbonyl synthesis. Now here I have shown you a couple of representative examples, carbonyl complexes. Nickel tetracarbonyl. Now you know that it's not a funny structure, it has a tetrahedral structure. And then you have a iron pentacarbonyl, right? You should have come across iron pentacarbonyl whenever we talk about the carbonyl base. And then chromium hexacarbonyl, and then metal bonded manganese carbonyl, cobalt, and osmium and iridium. So you don't need to bother about all these. These are the bimetallic carbonyls. So your syllabus is only limited to the monometallic carbonyls. Okay. Right. Now the question is that the very important thing. Right. Why do we study metal carbonyl? Why we should study metal carbonyl? That's a fundamental question. Some of you may have why sir we should study all these metal carbonyl? Is it really does any meaning? I will explain you why. Right? Why we are talking about the carbonyl. Earlier I mentioned somewhere that the bonding of the person who inhale carbon monoxide, right? What will happen? This person cannot live, right? If you are inhaling much of a carbon monoxide, what it happens? It goes and bond with your hemoglobin iron center, right? This bonding is two-way, as I have mentioned already, a sigma donation and pi acceptance. Sigma donation from the carbonyl to the metal center, and the pi acceptance from the metal center to the carbonyl. I hope all of you are with me. Earlier I mentioned this bond, you cannot simply break it. If you want to break it, the entire hemoglobin should be destroyed, right? Simply this bond cannot be. So what we say is that irreversible binding. Irreversible. But on the other hand, if you take oxygen is a reversible binding. So carbon monoxide irreversibly bind. Now you understand that why we are talking about the carbonyl. Much more than that, there's a biological. So unfortunately, we will not be teaching you bioinorganic chemistry because of the limited number of classes. We look at the organometallic aspect of the carbonyl. Right. Now, what we see here is that there are a lot of applications, the carbonyl. Say, for example, number one application is here, the hydroformylation, that is alkene to aldehyde. Right. I start with the alkene and I end up in getting a aldehyde. Okay. Now, basically what I do, a carbonylation, or what I use I use a metal complex. This is what we call the homogeneous catalysis. So this is what we'll be studying. This is one of the reactions, right? And then methanol to acetic acid, what we call the Monsanto acetic acid synthesis. Monsanto acetic acid synthesis, where what we have your carbonyl complex, rhodium carbonyl complex coming to picture there. So studying the carbonyl is not just for for fun. It has a lot of implication in the practical life. I mean the real life practical applications, right? I will go here, right? This is what I have the molecular orbital diagram. I have already explained to you. That is what I have a carbon and oxygen. It's a mere repetition of what I have already taught in the MOT. That is a heterodiatomic, right? Heteronuclear diatomic. The carbon monoxide I have taught. The same diagram is there. Your HOMO and your LUMO, right? LUMO is a empty, HOMO is a occupied. There is a sigma, there is a pi star orbital. These two are, I have already explained how the interaction takes place between sorry, let me put it this way. And here is your carbon, right? This is what we are talking about. This bonding we are talking about. Okay, right. So based on, you can explain only with the help of your MO theory, not with others. Okay, this I have already explained. I think we don't need to again explain. Now look at here. This one I have already explained. That is low oxidation state. CO can do the job, right? How CO can do the job? That is basically a pi back bonding, right? And the sigma donation. These two are, as a result, you have all these kind of nuclear tetracarbonyl, pentacarbonyl, hexacarbonyl, all the structure which I have already shown, right? Not new, everything is already I have shown, right? I mean here. These are the structure that I have shown here. I have listed here. Okay, right. Now, how do we synthesize? Yeah, very simple method. You start with your metallic nickel, carbon monoxide. You at a particular pressure, at a particular temperature, you get a nickel tetracarbonyl and also iron pentacarbonyl. And other methods also there. So from halides, you can easily synthesize your metal carbonyl. Okay, right. Nothing much to mug it up here. But I should tell how do we get the metal carbonyl complexes? Yeah, simple methods of direct carbonylation or reductive carbonylation. Direct carbonylation and both for the reductive carbonylation both have been widely used in the industry as well. Now coming to the important part of your organometallic chemistry. Okay. Anybody has any doubt? I hope all of you are with me.
Sir, in the above slide where you showed conversion of alkene to aldehyde, sir, CHO group will always attach to only one of the carbon, or it can attach to both any of the carbon of the alkene?
Yeah, we'll come to that. Basically, when you talk about the stereochemistry and the catalysis, I will come to the catalysis after I finish my electron counting. Then you will be able to understand that.
Okay, sir.
No, I can't hear. Your voice is not audible. Your voice is not audible. Okay, I mean, those who have a question, you can post in the chat box. I will look into that and I will answer your question if you have. At the end, I will give you a 5 minutes break, and then I will start and till my catalysis, and then I will finish the organometallic chemistry. I will give you a 3 to 4, maximum 5 minutes break. Okay, now it's 10:50. I will start at 10:55. Okay, if you have any questions, you can post in the chat box. Some of your microphone has a problem. I am not able to hear. If you have anything, you can put in the chat box.
Sir, I have posted in chat box. Can you check it?
You say that what do you say that, sir? If highest energy orbital has not any electron, then can we call it HOMO? No. I see highest occupied molecular orbital. When you look at that, I will go back. Right? Don't confuse. Don't confuse here. I mean, I don't know how you are. Highest occupied molecular orbital. That means the orbital which is in highest energy, which should be occupied, whether it's partially or fully occupied, then only we can call this a HOMO. Okay, so in the energy scale, when you're looking at that, which is the orbital at the highest energy level has occupied highest molecular orbital. Don't count the, I mean, it's not based on the.
Hello.
Yeah, tell me.
Sir, if higher.
No, I can't hear. Your voice is breaking. Your voice is breaking. Put in the chat box. Otherwise, you said check your microphone. I'm not able to hear. It's very simple that highest occupied molecular orbital. Your question is highest energy orbital has not any electron. Then can we call it as HOMO? No. If you don't have electron, that is automatically a unoccupied. Right? So there are two things: highest occupied, lowest unoccupied. There's a true classification because both of them has a lot of implication in the bonding. Highest occupied, which can donate, lowest unoccupied can accept. These are the implications. I hope you are getting. See, HOMO means again you are confused. Don't wrongly interpret the meaning. HOMO means highest occupied. That's all. There is no other definition. When you look at here, there is a three sigma. Sigma orbital. There is a 3 sigma. What I have encircled here is the. Let's see what I have I'm encircling here. This orbital is the one that is what I call as a highest occupied. There is no other definition at all. You are asking, sir, highest not occupied, then orbital just lower in energy and occupied can be. No, I'm not getting what you're asking. Right? It's very straightforward. Highest occupied.
Sir.
Pardon? Pardon?
Sir, if 3 sigma is not occupied, then can we call 1 pi HOMO?
Yeah, obviously, if the definition, that's a definition actually. If 3 sigma is not occupied, then obviously your highest occupied is a 1 pi. The lowest unoccupied will become a 3 sigma. That's all.
Okay, now I understand.
Okay, right. We'll go. Right. Now you need to listen very carefully. That is what we have is the 18 electron rule, which you should not have studied earlier. Right? Basically, what we have is the 18 electron rule. We need to count the number of electrons. I will briefly mention, and then tomorrow class, your tutorial teacher will systematically teach you. Okay? I repeat, All of you, please attend your tutorial class. There, the counting will be taught systematically. I will give an overview. What actually the 18 electron rule, what are the method available? I will not give you the problem to solve out here because we don't have time. Your tutorial teachers will teach you. Okay. So in the organic compounds, right, what we have is that you have an octet rule, right? I hope you remember, right? 8 electrons. That's S and P orbitals, right? S2 electron and P6. You have an 8 electron. Based on that, what we have an octet rule. In organometallic chemistry, what we have is we have an 18 electron rule. That is basically where it comes from. You have not only S, P, but also D. Say, for example, a 10 electron and 6 electron. So what we have is an 18 electron. The system in the sense, the organometallic complexes, which has 18 electron, are considered to be stable. But it is not a hard and stick rule. Only the 18 electron complexes will be stable. There are complexes which has 16 electron or sometimes 14 electron that also is stable. So basically, this is an inert electron configuration, right? Inert configuration. So what do we say? The stability comes from there. In the right hand side, I have shown one MO diagram. If you count the number of electrons, this is basically based on the LFT. That is a modified MO theory. That is what we say ligand field theory, right? What we say is that a ligand group orbitals and the metal orbital. Right? We are not going to talk about any bonding. Just to show you counting the electron. Right? Here I have a 4, and then I have a 2, 6, and then I have a 9, and then I have a I have a 6. And I have a 6. Totally what I have a 18 electron. If a metal complex has this configuration, electronic configuration, what I will say is that, yeah, what is considered is these are stable complexes. Yeah, basically comes from the inert gas configuration. Okay. Now, that's basically it goes the history. 1920, British chemist Sedgwick has formulated, and then further it is modified, and then you see here. Right. What I have already explained, octet rule. Already I have told that S electron and P electron, and then your 10 electron, you have your 18 electron, that is for the organometallic. In the case of your S and P, you have a 8 electron octet rule. Right. So this octet rule is basically valid only for that period 1 to non-metallic elements. Right. These are all fundamental. We are not going to study and take an example and work out. We are not going to do that. Basically, the transition metal, TM is a transition metal complex. Transition metal can add electrons from Lewis base in addition to its valence electron to a total of 18 electron. Right. Transition metal, that's you are talking about the D electrons, right? D. And then it can add further electron from the ligand. As I have mentioned, the metal carbonyl complex. What happened? Sigma donation from the carbonyl to your metal, that is added to the metal orbital. Then totally count should be 18. If that is the case, that system is considered to be a stable system. This is also known as effective atomic number rule. But is that it only apply to metal with low oxidation state, right? Low oxidation state. Now, I will be showing, right? Look very carefully, but I will not explain you much. We are not going to count anything. This table show you the number of electron donated by a ligand to the metal, which needs to be considered for counting the valence electron. What we are talking about? 18 electron count. Okay, 18 electron count. So you have a table. What is the charge? There are two methods. That is a neutral atom method and oxidation state method. So I would encourage you to go with a neutral atom method. Your tutorial teacher will be following neutral atom method. I suppose you stick to only one method. Right? Don't confuse between here. And if you're reading textbook, don't get confused. Some of the textbook will give you the oxygen state method. Some of them will give you a neutral atom method. Yeah, please stick to one method. Okay. So here and all I have given here is the number of electron donated. That is, if a carbonyl ligand is bonded to a metal, the carbonyl ligand donate 2 electrons, which should be counted. Right. Whenever you have one carbonyl, electron count to the 2 electrons should be counted. Right. Electron donated, that should be counted. There's a big table is there. Don't be afraid of looking at this many table. We need to mug it up. It's not that, because we don't talk about your hapticity. That is bridging ligand. Bridging ligand is not in your syllabus. Only a monometallic ligands. Say for example, halides, your aryl, alkyl, carbonyl, and your hydride, and your triphenyl phosphate, triphenyl PPH3, RPR3. So these are the common ligand that will come in your syllabus. Okay, your tutorial teacher will give you detailed explanation for this, and then come. Right, neutral atom method. I have given only one. I will take only one example. You forget about the second example. Right, rhodium example you forget it about. Look at the manganese pentacarbonyl. Right, a neutral atom method I have given. Yeah, manganese is 7 electron, valence electron, 5 carbonyl, 2 electron each, 10 electron, and the charge 1, it's a 1 electron. Totally you have 18 electron. Okay, I'm not going to explain this one here. Right, I hope you are following. What I'm doing is I am calculating the valence electron by a method, what I call the neutral atom method. How do I count it? Find out the valence electron, find out what are the ligand that is coordinated, and find out how many electrons are donating. The ligands donate to the metal, and look for the charges, if any, and totally add up together, that you get your electron. Another one example, what I have given here is the iron pentacarbonyl. Right, iron pentacarbonyl, 8 electron and 10 electron. Right, totally 18 electron. Right, I hope you are following. It's not a big deal at all. Then you come here. Again, don't say that sir has, I mean, flash the slide and left. Right, this will be taught by the tutorial teacher. I have given a representative example. Okay, now look at this example. Right, that we'll be dealing with. Okay. The rhodium complex, what I call the Wilkinson catalyst. Right, I have a 8 electron in the metal center because it has a +1 oxidation state, and then I have a 9 other electron basically coming here. 9 electron, right, is here. Totally I have a 16 electron. Now 18 versus 16. In the case of the iron pentacarbonyl, I have 18 electron. In the case of a rhodium complex, I have only 16 electron. Now, what I am going to call this is coordinated. The 18 electron is saturated. What does it mean saturated? There is no way you can add up more electron into that. Already it is saturated, coordinatively saturated. On the other hand, the rhodium complex is coordinatively unsaturated because it has only 16 electron. Stable configuration is, inert case configuration is 18. Here you have only 16 electron. Why I am calling this and then why I bring it here is that these complexes will be used as a catalyst in the homogeneous catalysis. Right? You wait for some time, you will be able to understand what I actually mean, the coordinatively unsaturation. Right? We'll go here. I will skip this one. Your tutorial teacher will give you all this explanation. Right, all this. Now we'll come to that. Okay, catalysis. You should have the introduction to catalysis. You should have come across. You should have at least read. Right. The right hand side I have shown the diagram, potential energy diagram. Delta G versus reaction coordinate. There one is catalyzed and another one is uncatalyzed. So when you have a catalyst, the activation energy required for the reaction is lower with respect to the reaction in the absence of a catalyst. Okay, this is the activation energy. There's activation energy barrier. Here it is decreased to some extent, to a large extent, that is in the presence of a catalyst. So the catalyst does not involve in the reaction. Catalyst only facilitate, right? Facilitate the electron transfer kinetic. As a result, as a result, what we have here is that your activation energy decrease. It may take the different paths. Okay, right. One thing you need to remember: it does not change the thermodynamics. Okay, thermodynamic remains same. Right, catalyst does not change the thermodynamics. Thermodynamic remains change. Now, when we talk about the catalysis, there are two categories: heterogeneous and homogeneous. Homogeneous in the sense everything is homogeneously distributed. Heterogeneous, I will give a typical example in the coming slides. Heterogeneous, you put two different phases: the solid phase and then your solid phase as well as in the liquid phase. Okay. Now, why do we talk about the catalysis? Yeah, synthesis of pharmaceutical chemistry in the pharmaceutical industry and agricultural, and another one is a catalytic converter, right? Say environmental, right? Or you should be remembering the catalytic converter, right? Catalytic converter. And then one is the synthesis of the chemicals. Second one is the catalytic converter. I will show you what it actually means. Biology, the enzymes are the best catalyst, efficient catalyst, efficient catalyst. And then what we're going to talk about, the organometallic compounds or the complexes, that is in the case of your pharmaceutical or the fine chemical synthesis. Yeah, these are some of the pictures. Be it, to explain, to make you understand the catalytic converter in the automobile. So how it works? They basically you have a platinum or the other metal catalysts are there, right? This is very common in the general chemistry textbook. You can understand that. We are not going to study the structure of catalytic converter. This is an example where heterogeneous catalysis is taking place. What is happening? That your platinum particles on the catalytic converter convert the harmful gaseous into a harmless water. That's the purpose of the catalytic converter. Right, again, it's the typical diagram. Right, here it goes. Your catalytic converter is here. That's basically a heterogeneous catalytic reaction that is taking place. Right, yeah. Again, we are not going to. You will go here. Right. How do I find out a catalyst? How do I select a catalyst? There are a few things that we need to remember. One is that activity, how efficient the catalyst, how good is the catalyst, right? And the right hand side, I have given you the rate of the reaction, how you follow that, how we efficiently catalyze. That one thing what we do is that a turnover frequency, right? What we call the TON, turnover frequency. That is the rate of the reaction divided by the concentration of the catalyst. That's what we call the turnover frequency. Larger turnover frequency is basically the efficient catalyst. Basically, what we say is that if I have a catalyst A, how many times it can undergo collision or catalyze that particular reaction in a single reaction container, the reaction mixture. How many times the same catalyst can be recycled again and again and again. That will define your activity or how efficient is the catalyst in terms of TON. What we say is the turnover number, right, or turnover frequency. Okay, here I mentioned about the turnover frequency. Then second one what we have is the selectivity. Selectivity, the lifetime, and cost. Of course, poisoning, right? Platinum catalyst will undergo poisoning, right? So usually platinum catalyst will undergo a irreversible binding. As a result, what will be the poisoning? Of course, selectivity, everybody needs the selective oxidation or selective reduction. And then how long this catalyst will be stable and how expensive the catalyst. All these determine the catalytic activity. right? So comparing different catalysts, catalyst life, catalyst efficiency, right? They're basically, yeah, there is a delay. There is a delay in the, okay, yeah, the turnover number and the turnover frequency. I got is a number of cycles for which the catalyst survives, right? Number of cycles for which the catalyst survive. Of course, your syllabus does not going to be any problems associated with the calculation associated with the turnover frequency and turnover number. We'll go to this one. We'll take what we'll study is that we'll have a two homogeneous catalytic reactions. One is the hydrogenation of alkene. Another one is the Monsanto acetic acid synthesis. We'll take two catalysts, organometallic complex, and study how the reaction proceeds and how the mechanism is controlled. Right? What's the mechanism involved in the catalytic reaction? Now, this slide, what we have is that the Nobel Prize winners. That's I've already mentioned that, right? Chemistry Nobel Prize winner is a 1973 Wilkinson. The Wilkinson catalyst I mentioned already. That's a rhodium, tris triphenyl phosphine Cl. Right? This is the catalyst that I'm talking about, the Wilkinson catalyst. He got the Nobel Prize in 1973, and many other the complexes are there. Those who synthesized, they received the Nobel Prize for their innovation. Right? Before going to the actual reaction, the two examples that I have given say that the hydrogenation of alkene and the Monsanto acetic acid synthesis. Okay, let me give you what are the steps involved. Number one is the ligand coordination or association. Right? I will give you examples. Oxidative addition, that's important. Migratory insertion, nucleophile attack, and reductive elimination. These are the four steps that is involved in a catalytic reaction that is happening in homogeneous solution. What are they? Ligand coordination, oxidative addition, migratory insertion, nucleophilic attack, reductive elimination. It doesn't mean that all the homogeneous catalytic reaction should have all the steps. Some of the steps may not be there. We'll come to that, right? Now, ligand coordination and association, right? Basically, what we have, say we have a metal, your incoming ligand and coordinates here, and at the beginning of the step, initial step. At the end of the step, what will happen? Bond will break, this will go, ligand dissociation, right? That's why we talk about the coordinatively unsaturated metal center is required. Coordinately unsaturated metal center is required for the homogeneous catalytic reaction, right? This is a very simple step, right? When I take the particular example hydrogenation, you will be able to understand what actually I mean. The oxidative addition, basically, they keep in mind. You can read through it and let me explain. Oxidative addition, what will happen? Whenever there is a metal center in the catalyst, during the oxidative addition, what happened? The oxidation state of the metal center increased by 2 units. That is, N goes to N plus 2, right? Say, for example, I have shown the rhodium plus 1. That's the initial oxidation state. During the oxidative addition, what happened? It goes to the plus 3 oxidation state. Plus 1 to plus 3. Now, what is the requirement for the oxidative addition? Now here, availability of a non-bonded electron density on the metal. That's mandatory. 2 vacant coordination site in the metal center. That's what I said, that coordinatively unsaturated. Unsaturation, like I mentioned, that is a 16 electron complex. Okay, a metal with a stable oxidation states separated by 2 units. Say, for example, I started with the M plus 1. Now I say that oxidative addition is taking place. Now it should go to M plus 1 to E plus 3. But I know that this metal at plus 3 oxidation state doesn't exist at all. That means this oxidative addition reaction does not go at all. That is, the oxidized species, after the oxidative addition, what we expect that the oxidation state of the metal center increased by 2 units, that should be stable enough, right? Let me give an example. What it here? Okay, what we have here is that you have this is the ligand that's incoming ligand, XY. Here I have a metal, right? The homogeneous catalyst. Then it coordinates here. Now it goes Mn plus 2. Okay. An example, a typical example is that iridium, bis triphenylphosphine, chloro, and carbonate. Now, what is the incoming ligand? Hydrogen. It goes and oxidatively add. As a result, what happened? +2 increase in the +2 oxidation state. That it happened. This is a simple step. This is one of the steps in a catalytic reaction. Okay, I hope you are not confusing. Very simple. Oxidative addition. What's supposed to be takes place? Increase in the oxidation state by 2 units. What is the requirement? The metal center, your metal center should be coordinatively unsaturated. If it is a 18 electron, you cannot have an oxidative addition reaction at the metal center. Another example, what I have shown here, iridium, that is 16 electron initially. Methyl bromide comes here, and then it goes here. Again, it is a 16 electron, right? Interaction takes place. Methyl goes here, and bromine comes out here. Is oxidative addition takes place. Now, at the end, what we have is that it become an 18 electron. At the end of oxidative addition, I repeat, at the end of the oxidative addition reaction, because one ligand is completely added, 16 become 18. I hope you are getting right. Again, this additional example already I have shown. This will come. This one will come back. Okay, right. Yeah, this is a repetition. What I have shown here. The third one. So number one, what I say is that association or dissociation. Number two is the oxidative addition. Number three is the migratory insertion. Look at carefully what is happening to migratory insertion. Suppose you have this complex, this one. What I'm talking about the migratory insertion. That is, look at here. Here I have a X and here I have a Y. The two ligands, which are both are coordinated at the metal center. Now, there is a process what I'm talking about. This Y go and insert between M and X. That is migratory insertion. I get this one. Okay. Obviously, at the end of these steps, basically what I did, I put in this way. Initially, this is Y and this is X. Now, what is happening? M. Here I have a Y and X. This position is become vacant. Right? Which position? Where initially Y was sitting over here. This position is vacant. Now, a ligand from the solution can come and coordinate here. That's what we have shown here, right? The second step, right? L plus, it goes here. Now, at the end of the day, what I have, MLYX, that is a migratorily inserted product that I am getting. Okay. So, one thing you need to remember, no change in the formal oxidation state. During the migratory insertion, nothing will happen. Okay, only the insertion takes place, no oxidation. It's not a redox process. Okay, that you keep in mind. One thing is that the migratory insertion to takes place, these two groups should be in a cis position. Right? Say, for example, look at the bottom one, what I have shown here. The methyl and the carbonyl. Methyl and the carbonyl both are in the cis position. As a result, I get a product here. That is a migratory inserted acyl group as inserted here. Now I have the product. Okay. The condition for migratory insertion is that the two ligand should be in the preferably there are exceptions. Right? Preferably in the cis position. Okay. This is, I think we don't need this one. This is a little bit of a stereochemistry. Yeah. This is basically the mechanism involved here. How the mechanism, right? We don't need it. Right. Now we'll go. Okay. Nucleophilic attack. Right. I will give you some time at the end of the class. You can ask the question if you are not able to follow. Another one step is the nucleophilic attack. If you have a pi complex like this, what I have shown here, if there is a pi complex of this kind, pi complex of this kind, right? What we can see here, a water molecule can go and attack. This is a very conventional reaction. It's not necessary that all the homogeneous catalytic reaction will have this nucleophilic attack. No, it's not the case. Okay, right. So this will, you will get another product, and so goes on, right? We will not be dealing with the nucleophilic attack in our homogeneous catalytic reaction, but we will be dealing with the association dissociation, oxidative addition, migratory insertion, right? So you need to remember what needs to be, what should be the criteria that is needed, what should be the requirement for oxidative addition, and what should be the requirement for a migratory insertion. Requirement for oxidative addition, basically what we have is that it should be coordinatively unsaturated. Migratory insertion, what should be? You should have both ligands should be in the cis position, preferably in the cis position. The last one, what we have, the reductive elimination. Reductive elimination is the last step. That is because you should get back your the catalyst and the products. So oxidative addition is the addition of ligand. Reductive elimination is the removal of an ligand. So what will happen? Just opposite of the oxidative addition will take place in the reductive elimination. What I mean, your oxidation state will decrease by 2 units. If it is +4, it will decrease by 2 units +2. Okay, so that is something that we need to understand here. Nothing much. So here you have a +4 platinum. The reductive elimination, you get a ethane molecule out of that from this complex, and then it is reduced to your platinum 2+. That's all. So what we need is that, what are the factors that facilitate the reductive elimination? Your high formal positive charge, obviously, that's what we say, that +4 state. The bulky group, you have, if you have a bulky group, say for example here I have a bulky ligand, it will be fissile. The reductive elimination will be fissile. And electronically stable organic product. What I mean by electronically stable organic product? This ethane as well as the complex, both should be stable, right? So these are the 3 requirements for the facilitated reductive elimination of the particular product. This example I will come to the hydroformylation and Cativa process. This Monsanto acetic acid synthesis, I will come in the second example. Okay, right. Now we'll take the first example. First example, I hope you are following. Are you with me?
Yes.
Yes. Okay. Right. Okay. Homogeneous hydrogenation of unsaturated hydrocarbon. I already mentioned about the Wilkinson catalyst. Again, I am not going to explain. The structure of this catalysis goes here. Again, I already shown you how this is the D8 configuration. D8 configuration, chlorotris, triphenyl phosphine, rhodium-1, typical nomenclature. Right. This is what is the crystal structure. How the X-ray diffraction crystal structure of this here. Right. This is the person, Geoffrey Wilkinson. Yeah, you can see the catalyst which he has synthesized still there in the Harvard University for display, put in a seal tube. It is still there. It's a major breakthrough at that time, right? He is the one got the Nobel Prize in 1973 for his innovation of synthesizing Wilkinson catalyst and using it for the homogeneous catalytic reaction. And the same modified catalyst has been used to synthesize one of the drug molecule. That's only drug molecule available to treat Parkinson disease. Can anybody say that what is a drug molecule to treat Parkinson? Anybody? Unmute your microphone and tell. Anybody knows? Nobody knows. Nobody understands. You know what is Parkinson disease? I hope you are listening to me. Yes? Nobody is listening.
So we don't know about the Parkinson's disease.
Yeah, Parkinson disease. There, basically, what we have is that the loss of motor control activity. That's very notorious. There's only one drug that is available, what we call the L-Dopa. L-Dopa, I have a slide at the end, I will show you that. That is basically based on Wilkinson catalyst. Based on, not this catalyst, based on this catalyst. So how do we synthesize? Rhodium trichloride, water, triphenyl phosphine. In ethanol at 78 degree, you get your rhodium triphenyl phosphine complex. Now it is commercially available. Now we'll go here. Right, simply follow it. Right, I'll already explain what are the steps involved. So now I will not explain again and again. I will give you the steps involved. You can easily understand. Okay. I hope everybody is with me. Don't sleep. Right. It's 11:30 only. Right. Rhodium +1. Okay. The first step is the oxidative addition. What is the reaction that we are talking about? Alkene hydrogenation. Alkene hydrogenation. Okay. So what you need is that you need hydrogen. So initial oxidative addition, that is goes here. Don't bother about the stereochemistry. Your syllabus does not have the stereochemistry. So we'll talk only the actual concept. You have your rhodium +1 is obviously converted to rhodium +3. That's what we call the oxidative addition. Increase in the oxidation state by +2 unit. This is the 16 electron species. Okay, that's why oxidation addition is possible. Now what happened? Ligand dissociation. Right? Ligand. Why the ligand dissociation should take place? You have an alkene, right? Basically, you have an alkene. This alkene has to come and interact with this complex if this is the catalyst. So already this coordination sphere is complete. 1, 2, 3, 4, 5, and 6 is already a hexa-coordinated complex. Now what's supposed to happen is one of the triphenyl phosphine ligand dissociates and create a vacant spaces. Vacant space that is created. Now this is the vacant with the complex with the vacant space. Now what happened? Ligand association. Right? Your alkene comes here. Right? And then coordinate. Yeah, pi complex. This is what I have mentioned, that pi complex. Right? This is what the pi complex. That is after the association of your alkene ligand to the metal center. Okay. Right. The first, I repeat again, oxidative addition, ligand dissociation takes place. It can take place in 2 separate steps, or it will take simultaneously. Okay. And then ligand association, that is ligand get the pi complex formation. And then what we have, the migration, or what we call the insertion. Migration or insertion taking place, where what we have, your alkene is here and your hydrogen is here. Okay. A migratory insertion or is a migration or insertion, and you get a complex of this type. Okay. Now, ligand association. Now, what we have, one of the ligand is dissociated here, right? Just here one ligand is dissociated. Triphenyl phosphine ligand is dissociated. It cannot go away somewhere, right? If it goes somewhere, you cannot get back the catalyst. You cannot call that as a catalysis at all. Now, what is the ligand that is dissociated from the metal center? Come and associate, right? The same ligand comes and coordinate, and I have a big complex, right? A complex of this type is there. After migratory insertion takes place, ligand is associated, right? The coordination, if you look at the coordination number, 1, 2, 3, 4, 5, and 6. I'm not violating anything. Okay. Now, this is the ligand association. Now, the last step should be, what should be the last step? Anybody? If you are following me.
Removal of ethane.
Yeah, removal of ethane. What do you call that step, Sony?
Reductive
Reductive elimination. That is basically this ligand should go away, right? That's one of the requirement. We say that for the facile reductive elimination, you should have a bulky ligand, right? Hope you can recall. You have a bulky ligand of triphenylphosphine here and here. As a result, in a facile or facilitated reductive elimination, it goes here. Now I got the hydrogenated product and then I got back my original catalyst. Hey Satyam, in the background something is going on. You are not attending the class, right? You are listening to something. Okay. So reductive elimination. I hope you got it. What I mean the hydrogenation of alkane. Hydrogenation of alkane. Right. Can I repeat once again? Do you have any question?
Sir, I have means when PPH3 leaves from the 18 electron complex, then we have one more complex formed in which RH is bonded to Cl, two PPH3 molecules and two hydrogen atoms. So is that a 16 electron complex with RH plus 3? So is it stable? No, above slide, sir, above slide.
This one?
No, 49. Slide 49.
Slide number 49. Yes, okay.
The complex in blue box and the in ligand dissociation part. So
yeah,
this is a 16 electron complex with plus 3 oxidation state.
Yes, right. Now what happened is that it doesn't happen. It means that it is step by step it is there. This process takes place within the reaction mixture in a particular time period. These are all at a particular condition. The intermediate species are, I mean, separated and studied. So at a particular condition, it is stable, but it doesn't mean that it will be stable for for example, 2 hours, 3 hours, 4 hours. The reaction mechanism is deduced based on the product in each steps, right? Those who study the organic reaction mechanism or catalytic reaction mechanism will understand. Yes, this is stable at this condition. It doesn't mean that it is stable like a other 18 electron complex. No, because as I already said that the oxidation state is higher oxidation state. So immediately, as soon as your triphenylphosphine ligand leave from the metal center, who is there at the behind this one? Your other ligand, incoming ligand is ready to occupy the place, right? So it leaves and then another one come and occupies. Like it's not that the seat will be vacant for a lot of time. Immediately it comes here. And then, but there is a vacant position. That species have been isolated and studied. Otherwise, the mechanisms cannot be established. Right?
Okay, sir.
Right.
Understood.
Okay. Sir, in step 4, migration or insertion.
Yes, migrate insertion. Yeah.
How many electron compound is that reactant?
Reactant, which one you're talking about? The third step or the fourth step?
In third step, it's the product.
The product of the third step.
Yes, sir.
Right. Now you yourself can count the number of electrons by the oxidation state method, right? Neutral atom method. Neutral atom method. You find out what is the valence electron for rhodium. How many electrons? What are the ligands are there? How many electrons there is count here? It goes again. The question will come there, sir. These many species are there. Now number of electron goes here. Whether this will be stable? Yeah, that's a what happens? Your association takes place. Immediately, what happens? A migrate insertion takes place. So it's not that you will have a 1 hour time to find out. Yeah, this pi ligand is going and attaching. Okay, now I have a octagonal complex. By this way, I will take out, and then it's not that. instantly taking place. Yeah, association takes place immediately, migrate, unless otherwise you freeze the reaction. Right?
Okay.
Okay, right. You can count the number of electrons. Number of electrons is no problem. Right?
Even for pi bond, we should consider as 2 electrons.
Yes, because I have already shown the table. Tomorrow, your tutorial teacher will tell you the pi bond, right? Alkene donation is the table. With the table, your teacher will teach you how to count the number of electrons. Then you can do that. It will not exceed. Say, for example, let me put that. You count the number of electrons. It coming into odd number. Say, for example, 15 or 70. Then either your counting is wrong or the species doesn't exist at all. That you keep in mind. Either it can be 14 or it can be 16 or it can be 18. Okay, that's a thumb rule, right? Tomorrow you will hear from your tutorial teacher much on that one. Okay, okay, right. We have another 25, 30 minutes. Yeah. Now, let me put some question, right? Let me put a question. What I have taken is that rhodium triphenylphosphine ligands. Okay. Now, if I use in the place of triphenylphosphine ligands, alkyl phosphine, right? PR3. Okay. In the place of a triphenylphosphine, if I take a trialkyl, what will happen to the catalytic reaction?
So if the alkyl group is not too much bulky, then it will not leave the final product, in last step, I guess.
Very good, Bajaj. And basically, there's an electronic effect is coming there. There are two, bulk steric effect as well as the electronic effects, right? Alkyl, because PR3 is not a good leaving group. In one step, we say that one of the ligands should dissociate and then come and associate. So PR3 ligand, sorry, not RR3, PR3. PR3 ligand is not a good ligand. So the rate of the reaction will decrease if you have a PR3. And another one, right? If I carry out this reaction, entire reaction of hydrogenation, in the presence of excess of triphenylphosphine ligands, I repeat, I have a round bottom flask, right? That's my reaction vessel. Here, what I have a catalyst, that is Wilkinson catalyst. I have an alkene. I have H2. Usually, the reaction is conducted in benzene. Along with that, I have an excess of triphenylphosphine ligand. Okay. Can you tell me what will happen to the reaction? Anybody? Quickly, we'll go to the next one. Anybody?
Rate of reaction will increase.
Rate of the reaction will
increase.
Increase. A very good answer. Really? How it will increase? Tell me. Bajaj. No problem. I mean, Sony or Bajaj? Who told? No problem. Don't worry. Sony.
Current told. I think current told the answer.
Yeah.
Sir, I think there will be too many PPS3, so probability of living and joining will be more.
Okay, I will bring another one. I will show you. Right. See, so look at the second step, the dissociation. Okay, this is mandatory for the association of your alkene complex. Yes or no? Answer me.
Yes, sir.
Yes.
Yes.
If I have an excess of triphenylphosphine, the equilibrium will be shifted to where?
So right.
Yeah, this side will go. Right, your dissociation will be suppressed. Dissociation will not take place if I have an excess. The equilibrium will be shifted to the complex, the original complex after the oxidative addition. So your ligand, your alkene cannot come and coordinate, As a result, the rate of the reaction will be decreasing. This is one of the proof that a ligand dissociation takes place after or before. In the sequence of reaction, ligand dissociation takes place. If I have an excess of triphenyl phosphine, the rate of the reaction goes down simply because the equilibrium is shifted to the other side. There is no room for the association of the alkene with the central metal atom. Right, I hope you got it. These are the tips, right? Applications, large-scale organic synthesis. As I mentioned, it is highly sensitive to the nature of the phosphine ligand, right? I hope I have slides. Right, you can see here the rate of the reaction, how it goes. Look at the table. Here is a simple alkene, 31.6, and then you have a bulky one. Here you have a 9.9, 1.8, and 0.6, and less than 0.1 because highly bulky. Because this pi ligand cannot go on associate with your rhodium. As a result, almost nil reaction is nil. Okay. So here comes the
Sir,
tell me.
What do we mean by nature of phosphine ligand?
Yeah, nature of phosphine ligand. That's what I have explained.
Means what is the this is the nature of alkene.
This alkene. Phosphine ligand is nature is, I already explained you. Say for example, I have a alkyl phosphorus. Sorry. I have a phosphorus. Here I have this is alkyl. Say for example, I have R. Okay. Or I have a bulky group in the place of, say for example, in the place of the P, here I have a bulky ligand, right? Aryl or naphthyl or any other aromatic, right? I will show the ligand that is used for the synthesis of L-DOPA. Then you will be able to understand what I mean with the nature of the. Right? So as the chain length increases, your dissociation will not take place at all. The rate of the reaction suppressed. Or you branch it here. This is the nature I am talking about. Instead of talking here triphenyl phosphine, here pH, and pH. What I do, I replace the phenyl group with other ligands. Either it's alkyl or bulky aryl, say naphthyl, or any other ligand that I am bringing in here. Based on the nature of the triphenyl phosphine, the rate of the reaction is determined. I hope you got it.
So smaller will be the size of alkyl group, faster will be reaction.
There are two cases. One is steric as well as the electronic effects. Two effects need to be there. Steric, it comes here. If I bring say for example, alkyl, long chain alkyl, the electronic effect will come and play. It will not undergo dissociation. With respect to your simple triphenyl phosphine ligand, both needs to be taken into account. Your steric factor as well as the electronic factor. Okay. Right.
Okay, sir.
Now, now we see here, this is the person, Noels. He got the Nobel Prize for the L-DOPA synthesis, L-DOPA synthesis, and this is the L-DOPA, right? That's an amino acid, the only drug that is available to treat the Parkinson disease. I have given already here, right? You can read it out. Now, how it is synthesized? Now you will understand the nature of the ligand, right? This is the nature of the ligand that I am talking about, right? Nature of the ligand. You see, this is a chiral ligand. It's a bulky ligand, but it's a chiral ligand. It's a chiral ligand. I think I'm killing the color. Okay. Now this is the what I have. What do we call the DIPAMP? Right. Don't bother about the nomenclature. I can give it, but it's not required for you. It's a chiral ligand. You start with here. 100% yield. You are getting with this one. Basically, catalysis is a simple homogeneous catalytic reaction involving Wilkinson catalyst. Metal center is rhodium. The process, concept, everything is the same, but only changes the ligand is changed. As a result, you get a 95% enantiomeric excess of the L-DOPA. It's a very tough job, right? No other substitute for this catalyst, right? So now we have L-DOPA in the industry, pharmaceutical industry, simply because of Wilkinson and Noels, right? Both of them has the contribution. Catalysis in the Wilkinson, and the ligand is modified by Noels, and got the L-dopa. Right, those who are really interested, you can go here. I have given all the details of the further development. Right, here it goes, a catalyst, and then enantiomeric excess, and then further convert final product is this one, right, L-dopa. Right, don't worry, you don't need to mug it up anything. It's just an example. But you remember the concept. The concept is very important. Okay, right. I hope you understand. Finally, it's not the final of the last of this class, just the homogeneous reaction. Last step, I have put in this way: oxidative addition, ligand dissociation, alkene coordination, migratory insertion, ligand association, and reductive elimination. Finally, I get back my catalyst. Otherwise, if I'm not getting back, I cannot call this as a catalysis. Right? I should get back. Okay, it's a loop, right? This catalyst, the red box catalyst should be available for n number of time. See, if it is available for say for example 10 cycles, the turnover number is low. I will say that catalyst is not very efficient. So if it is able to cycle again and again as many as number, then I can call this catalyst as a efficient catalyst. Usually rhodium catalysis. Rhodium, the Wilkinson catalyst is highly efficient, right? Now you don't need to confuse. A simple, right? Start with the Wilkinson catalyst, oxidative addition, increase the oxidation state by 2, and then one of the ligand dissociate, and then in the dissociated place, a vacant position is there. A alkene goes and coordinate, and then followed by a migratory insertion, and followed by a ligand association. That is the ligand that is left out here. The dissociated that comes here, and then you get your product finally after your reductive elimination reaction. Okay. Okay.
Sir, so in this, when we use Wilkinson catalyst, always scene addition of H takes place.
Yeah, right. I did not go to. I thought I will go there because your syllabus does not have the to have the stereochemistry. So we will not be talking about the stereochemistry here at all. That's a little elaboration. We need to have additionally at least 2-3 classes to explain and bring example how it is happening. A trans effect is here, sin addition is there. All this coming to picture there. What you said is correct, but I will not be discussing in the class. It is, I mean, some of you will be able to easily pick it up. Other students may not be able to pick it up. Anyway, it's not in the syllabus, right? I'm not talking about the stereochemistry at all. Again, it's not the paper and pencil exam for you. It's simply a bubbling, right? A product will be given. You need to choose, or you need to maybe a simple, right? What is the product of this reaction? Either you write or bubble. So I mean, anyway, this is not in your syllabus. I can teach, but it is not in your syllabus. So let us not go to the stereochemistry. Okay, right. Now we'll talk about the acetic acid. Let me sip up a cup of water. Okay. Right. Acetic acid. I have given a big table, right? Big flow chart where and all acetic acid is used. Important industrial chemical, I am not going to teach a history or the industrial chemistry topic. Just to tell you that acetic acid is very important, as you should be knowing. 8 million tons is produced all over the world annually. So what is needed? We are looking for the catalyst which can catalyze the conversion of something to acetic acid. Wait for some time, you'll be able to see that, right? Traditional synthesis uses bio-oxidation of ethanol, right, via fermentation process. You should have heard about the fermentation process, right? Yeah, you go here, you go get here ethanol, you get here, and then you ethanol, and then you go ethanol to acetic acid. But this is not a very efficient process, and also it's not a very clean. Lot of hurdles there. Industrial process is basically methanol, and carbonylate this methanol and convert into acetic acid. That is what we call the carbonylation. Carbonylation of methanol. Okay, carbonylation of methanol. We need a catalyst. Basically, we have a same the rhodium metal, but we have the rhodium catalyst. Okay. This process, what we call, is a Monsanto process. One who developed this one, a Monsanto process. Another one process is there, Cativa, that involve Cativa process involves the iridium complex. So we are not going to talk about the Cativa process. We talk only about the Monsanto process. Okay. Yeah, carbonylation of methanol to give you acetic acid. Carbonylation of alkene, right? And that also can give you a corresponding acid, right? If you start with here, you will be able to get here, right? Cobalt post catalyst, basically what we call the BASF process. Again, we will not be learning that one. That is before 1970 that has been used. From 1970 onwards, Monsanto commercialized rhodium carbonyl iodide catalyst, and it is commonly called the Monsanto acetic acid process. Okay, so not get confused. What we do here is we use a homogeneous catalyst based on rhodium to convert or carbonylate a substrate to synthesize acetic acid. Okay, I hope you are getting right. Yeah.
Sir, in carbonylation of alkenes and alkynes, where is that CO attached? In between of double bond or?
Yeah, just hold on. You are asking me before I make the foundation, right? Carbonylation, right? This process, the carbonylation of alkene is a complex process. You hold on, right? It is not in your syllabus, but I can explain you. Maybe either at the end of this class, if time permits, or the next class. I will explain you today the carbonylation of alcohol, right? How we go there, right?
Okay.
Right? I mean, I can keep on teaching. I'm fascinated to teach, but it is not in our syllabus, and we don't have a time. But I will explain you either at the end of the class, or I will briefly mention, not completely, right? Because that mechanism is, I mean, not required for you. Okay, right. Now, what you're going to take is, yeah, little. I hope you are able to see. All of you are able to see that, right? I have a catalytic cycle also. I will bring that later. First, let me explain you the possible mechanism. So what we are talking about here, please all of you listen. Now I have only 117 students left, right? Right. This is the problem. Okay. What I have, I am converting my methanol to acetic acid. This is the process that I am talking about. Okay. Right. Now, what happened? The first step. Okay. You need, that is not only one catalyst. We are talking about the rhodium. Basically, your rhodium based catalyst. And what I have is a hydrogen iodide. Now, what happens here in the first one is a methanol reacts with hydrogen iodide. You get a methyl iodide. Okay. And then what we have, what we have, this is a 16 electron complex. Now, what we have, a methyl iodide comes in here. This is a catalyst, 16 electron complex. The oxidative addition takes place here. What is getting added? Your CH3 and I. So the methyl iodide is oxidatively added. This is the RDS. Okay, you will not study the kinetics part. Oxidation. Now, guests are waiting to join. Who are the guests waiting to join? I don't need to admit anybody. Okay, let's forget about this. Right, oxidative addition, and then what you get? 18 electron species. Very similar to the oxidative addition that we have seen earlier. That we have here is the oxidative addition of. There you have oxidative addition of hydrogen. Here what I have here is that oxidative addition of your methyl iodide. Now, the third step, a CO insertion, right? Migratory insertion. This is the oxidative addition. This is a migratory insertion that is taking place. Now you have here what I have, CO insertion or alkyl migration. We can call it as a CO insertion or alkyl migration. I would call that migratory insertion. No problem, right? What we have here is that a 16 electron complex of this kind. Okay. Then now what I have, the coordination of a carbonite that comes into picture. Then I have a carbonite 18 electron species of this kind. And then for last step, what I have is a reductive elimination. That is, I got the catalyst back, and what I got is, instead of acetic acid, what I got is that I got the CH3 C double bond O I. This is what I got. Okay, this in the presence of water convert into your acetic CH3 COOH plus HI. I hope you understand the beauty. I need the HI for the next cycle. I initially started with a methanol and hydrogen iodide and the catalyst. What I call the hydrogen iodide is basically a co-catalyst. Co-catalyst. I don't know who is waiting for me to join. I don't need to allow anybody. I already allowed you. Okay, let me there. Okay, right. Yeah, let me go to the cycle. I will explain you again. Either today or next class. Once again, I will explain it before I start the next class. Okay. Right. Now look at the cycle. Look at the cycle. Look at the cycle. Initially, what is happening? Look at the yellow rectangle. Methanol, carbon monoxide, your catalyst. Right. That is an entire catalytic reaction that comes here. Who is that? My goodness. Right. Keep on disturbing. Okay. Now, what are the steps that are involved? Oxidative addition. What is the oxidative addition? What is happening? Now you see here methanol. Right, methanol. It's getting converted into methyl iodide. That's the first step. It is taking place in the presence of the co-catalyst hydrogen iodide. Now it is getting converted in methyl iodide. Now methyl iodide comes here. An oxidative addition is taking place. Oxidative addition, and then you get your 16 electron complex become an 18 electron complex after the oxidative addition. So what will happen? The oxidation state is increased by 2 units. As a result, what we have here, the 16 become 18, and then a migratory insertion, that is your carbonyl insertion or alkyl migration, right? It goes here. Now this is the migratorily inserted product, 16 electron. Now this carbon monoxide is that's mandatory because we talk about the carbonylation, right? There we need a hydrogen. Here we need the carbonyl ligand, carbonylation. This associate, you get your 18 electron species. Then your reductive elimination produces your the acyl complex, right? Which undergo hydrolysis or in the presence of water, give you acetic acid, regenerate your hydrogen iodide and your original complex, that is you have used in the I don't know who is waiting for I don't know who is waiting, no idea. Chirag, okay, I don't know why he needs need my permission to come here. Okay, yeah, okay. Right. Okay, right. I hope I have explained. Again, once again, we have another 2-3 minutes before I have not concluded. I will come back to this again in the next class. You have a next class after 12 o'clock. You have any class now? Sony?
Sir, we have class at 3.
Class at 3. Right. I will finish in 5 minutes. and I'll give time to for discussion if anything is there. Then beyond that, I will not take it. Right? Let me explain once again. Everybody understood the cycle? Instead of repeating, let me ask. Right? If you have any doubt anywhere in the catalytic cycle, now you ask me. I will explain. That's the best way.
Sir, once explain after association.
After association, in this cycle, right?
Yes, sir.
Okay, right. So your migrant insertion, you are putting your acyl complex, and then carbon monoxide come into here because that is mandatory, because it's a carbonylation of methanol, right? Now, what you are getting is that your association takes place. You get a complex which have 18 electron. Okay. Now, what should happen? A reductive elimination should happen in order to get back your catalyst as well as your products. So reductive elimination, what are the requirements? I have already been listed. Right, the requirements are there. Right now, the after association, it will get 18 electron, and the next step immediately once the carbonyl is come and associate with the rhodium, immediately, or what will happen is that your CH3COI, this group should leave from here, generating back your catalyst. That's what I call the reductive elimination. What is this name? Right. Chirag, you asked me to admit. Now you are coming and playing music for us. You want to entertain us, everybody? You do after the class, right?
Okay.
It's not okay, right? It's serious. You are listening to a music, right? During the class. I have no problem, but little be serious during the class.
Okay.
Okay.
It sounds very good.
Pardon? What is that?
Sir, he is an intruder. He is from outside.
Yes, sir. He is not Chirag. He is trying to.
Yes, sir.
He is not real, sir. Yes, sir. Someone is
Yes,
impersonating.
sir.
Really?
He's not
Yes, sir. He is from outsider.
My goodness. This is
He is not from
Not from
ITKGP.
correct.
My goodness. What is this?
Remove him from the meeting.
Huh?
Remove him from meetings.
Just let me find.
Somebody came in another class.
This Chirag goes, right?
Guest, sir. Chirag Ghosh guest.
How do I remove this
But
guy?
if it was Chirag, he would have a roll number. Institute. This guy has no roll number.
Chirag goes doesn't have a roll number. Oh, I made a mistake, nah?
Chirag must have a roll number. This person doesn't have a roll number.
Actually, sir, by using his name, any other person has came to the meeting from outside.
That's a problem. That's a problem.
By
Okay.
impersonating him, someone is trying to defame him.
Yeah. This is. I mean, last semester something happened. They took the video and then make something and then put on the social media. So many things happen, right? This is Chirag Ghosh. Let me note it down. Chirag Ghosh. He used his Chirag Ghosh. Okay. Just a minute, please. I should not have admitted this guy. Okay, right. Okay, right. Yeah, I was in the middle, right? You get back to your catalyst, and then your CH3COI, which undergo hydrolysis, you get your acetic acid and hydrogen iodide and water, right? You got it, or you have any doubts? It's a kind of a disturbance in the middle.
Got it.
Got it. Okay. Anybody else? Any doubt?
No, sir. Got it, sir.
Okay. Either in the previous catalytic cycle or in this cycle, anybody has a doubt?
Sir, so whatever you have taught till now, that will be the syllabus of assignment 1?
No, Sony. I mentioned, right? The
Before organometallic.
assignment 1 is the MOT, CFT, and Chelate effect. The organometallics and your redox reaction, is the second assignment.
Okay, sir.
And so the complete part of inorganic chemistry will be in end sem.
Yeah, right. Because last semester we had it. Before that we have taken, but the students have complained, and then now it is a mid sem and the end sem. So what we'll have is that we will have the end sem will have your